Hello to everybody and welcome to our webinar number 1 in 2022. Welcome to all those of you who have already attended our webinar series in 2021. We are pleased that you have joined us again today. It seems you liked it. And a special welcome, of course, to all those of you who are listening for the first time. Now, let me first briefly introduce our team to you. My name is Sibylle Hildner-Lippold. My profession is translator and interpreter with focus on economics. I work with the company since 1997. So this year I'm celebrating my 25 years here. I'm part of the MIM sales team, and here I'm mainly responsible for our international markets, like Italy and France. Bernhard Heil graduated in mechanical engineering at the Technical University of Karlsruhe. He joined our company in 2012 as project manager. In this function, he is the technical counterpart and interface between your development and our production. Mario Lang started his professional career with a solid 3 years apprenticeship as a tool mechanic, specializing in milling technology. Subsequently, he acquired a degree as certified technician, and in the year 2000, he joined our company as a project manager. Since 2005, he has the function of a technical sales manager and is today responsible for the sectors aerospace, medical technology, as well as luxury and consumer goods. Now, before we start, here's some general information for you. I will first briefly introduce the company to you, and then we'll go on with the presentation. During the presentation, all participants are muted. So please do use the chat function in case you have questions or comments. Also, during the presentation already, you can use the chat function, because directly after the presentation, we will do a questions and answers round where Bernhard and Mario will answer your questions. So now let's get started. MIMplus Technologies is an experienced and innovative manufacturer of metal parts and assemblies, and our focus is on high-tech materials. We belong to the OBE Holding Corporation with production sites in Germany and China. The company has been founded in 1904. So today we have 118 years of experience in precision engineering. We have 500 employees in the world and a worldwide production floor capacity of 25,000 square meters, among which 5,000 are dedicated for the site of MIMplus here in Germany. So here are some key facts on our company. We deliver over 25 million parts and assemblies per year. Our customers come from really different industries, such as medical, aerospace, automotive, and luxury. Our core technologies are MIM and AM. We offer also complementary technologies like CNC machining, investment casting, stamping, and assembly. We offer also various post-processings, which is, for example, tumbling, sandblasting, polishing, or also electroplating. We offer also PVD and DLC coating and laser marking. Other strong points are that we have our in-house tool shop and our own machine construction and automation. And we dispose of a research and development department with a very well-equipped laboratory. We work with a network of leading suppliers. here you can see some of our certificates. We have the ISO 9001. We are certified according to the IATF 16949 for the automotive sector. And we are proud to tell that our new certificate for the medical technology, which we have since February 22, the ISO 13485. So the topic of our today's webinar is MIM and AM in the medical industry. We will show how the use of additive manufacturing and metal injection molding can provide a higher design freedom for developers in terms of shape and material. I'm handing over to my colleague Bernhard now, so enjoy the presentation.
So, hello everybody. I'm glad to explain you something about MIM and AM. And I just wanted to start this thematic in this way. If you want to be fast, you have to choose the right vehicle for this. But don't forget that it must fit to the road. So the conclusion is the selected production process must fit to your parts, to your form and your function of the parts. And the process is only as good as it fits to the part you have to produce. So now that's the way to the processes we can offer to you. It's starting with a raw material, as I think every production process in the world will start. In our case, it's a mixture of metal powder and binder. And of this raw material, we make a shaping. And now we can offer you different ways or technologies to make the shape. So one, the more older thing is the MIM. That's the shaping by an injection molding machine, which is quite well known. And the more newer technology is the AM or additive manufacturing technologies, where we have different ways to form the parts in-house. After that, after shaping the so-called green part, you have a deep binding process. That means you remove most of the binder and leave the metal powder in the part. And after that, you do the sintering process, which forms out of the powder a complete metal part. So, more to explain the additive manufacturing, one technology we have in-house is the so-called cold metal fusion process. So what's that like? You have a powder, a bed of powder. This powder is the metal powder, which is surrounded by a thin layer of plastic. And you use a laser with conventional 3D laser printers. And you melt off the plastic, and by melting off the plastic, you have a fixture between the different metal powders. And so you can form a thin layer of your part. After that, you have a roller and you add the next layer of feedstock, you laser them, and in this way you build up your part layer by layer. The opportunity of this is you don't need support structures, because you have the bed of the powder surrounding your part and giving the stability to this. And you can use the cheap conventionally 3D printers. After that, of course, you have to remove the loose feedstock, the rest of the powder, then do the debinding and the sintering to get your metal part. At the end, I think at every process we can offer to you, you have a high density metal part with a closed porosity. The sinter shrinkage in this process is around about 13%, and you have quite robust green parts, so you can do some green part processing with them, like drilling or other processes, maybe some processes to make a better shape, to not have the big surfaces between the layer and so on. The next process to make the AM green part is the mold jet process. In this process, you print a wax-based mold and you fill the mold layer by layer with a metal paste. And so you have a better surface quality than in the our process. And you have as well no support structure necessary because you have a mold out of a wax-based mold. And this process is quite efficient for a high number of parts. After that, of course, you have to remove the mold. So it's melting off and then do the binding and the sintering of the part. Density is approximately 96%, so comparable to MIM and the other process. And sinter shrinkage is approximately 14%, so nearly the same. And of course, the MIM process, so you do the metal injection molding of the feedstock in a conventional mold tool, and you plastify it, inject it, and so you get a part in the conventional way. It's quite a fast process compared to the AM processes. And okay, but it needs the mold, and so it's for low values, for low numbers, it's not a perfect process. After having shaped your feedstock or have your green parts and debind it, you have the sintering process, which is heating up the part and remove the rest binder and then heating up to sinter temperature, which is near the around about 1300 degrees Celsius. And then you sinter the parts together, you remove the porosity of the parts and you get the dense sinter parts. Of course, in this process step, you have only low strength of your part, and you have the shrinkage, and you have the friction between your sinter plate and so on, and you have to think of how can the part deform in this process and what can you do to avoid this. That's something you have to think of in the design. Okay, and now if you know the process and its advantages and its challenges, it's some words for the design of the part. So conventionally designed thinking, as you know it from milling or so on, it's like Michelangelo said, you have a block of your part and you carve away everything that you don't want to have, and you carve away as less as possible because it's costing you time, costing you money. If you think about AM or think about MIM, it's quite a different way of thinking. You don't think of a block which you have to remove some material. You think of your function you have and to add the material there where the functions needs it. And it's quite the opposite look on the part or on the function you need. And below you see two parts that have the same function, but a quite different design, because on the left side you have the machine design, you have the massive block and only remove the functional areas. And on the right side you have the MIM and AM design, you have the functional areas and then combine them with as less material as possible just to get the strength you need for your function. So if you compare the different processes, the MIM is the best one for the high volumes because its shaping is very fast, it's very cost efficient compared to the AM parts, but you need a tool and the tool is expensive. So if you have only low volumes, the AM is the better process because you don't need a tool. Surface quality, the best way is MIM because you can create the tool very, very exact with a very, very good shape. That's not that good in the layer-based 3D printing process. But of course, if you are thinking in MIM, if you think of a mold, you need demoldable design, demoldable cavities to make. And that's something you don't need in the AM process. So you have more design freedom in the AM process because you're not limited by a tool. It's just another slide to show you with some numbers the MIM is. Let's say we'll start around about 5,000 parts per year and go up to more than 1 million parts. The size of the parts is quite small, maybe starting at a few millimeters, going up to 100 millimeter maybe. Then the mold jet is for the numbers, maybe 100 up to 10,000 parts per year. And it's always suitable for a big range of parts. And the cold metal fusion process is a little more for the bigger parts because it's not so exact in its layer thickness than it's the mold jet. And of course, if you have the bigger parts, it's quite for the smaller numbers of parts. Part complexity is, I think, comparable with a little advantage for the mold jet and the cold metal fusion combined to the MIM because you don't need a mold and you can use non-demoldable cavities. Yeah, if you think about the material you can use in the different processes, so of course, because it's long time used, the MIM has the biggest range of materials that are available at the moment. But in the AM, I think mostly used materials are available as well as the stainless steel. Of course, low alloy steel actually is only available in MIM. Tool steel is only in MIM available, but is under development in cold metal fusion and mold jet. And so actually, cold metal fusion, you can get super alloys like Inconel or Stellite or titanium alloys as well. And the rest, mold jet, is only available stainless steel at the moment. Well, one specialty is the hard magnets made of neodymium iron ore. That's only available in MIM at the moment. I think it's a specialty of MIMplus because as far as I know, we are the only company in the world that can offer you a neodymium iron ore magnet in MIM, actually. So the conclusion of all this, sinter-based AM and MIM is capable for producing complex metal parts. We can offer you all of these technologies now. Each technology has its pros and its cons, so they are not struggling for the same part. You have to think over the part, which is the best process for your part, your needs. And so they are complementary and not for the same one. So that's the finish of my part. And now I will hand over to Mario.
Thank you, Bernard. So, warm welcome also from my side. Well, I have not to say only hello, I have to say also good morning. We have participants from 30 nations here in this meeting today. So it is quite impressive. So I hope you fulfill your expectations on this. I would like to start with the products we supply today in the medical industry. The first area is, of course, for dental and orthodontics. There are quite different dental products. The handles, they are, of course, high precision parts, but they have also cosmetic requirements. Orthodontics, they are, of course, much smaller than the handles. They have also surface requirements, but not in a cosmetic. They are more in the technical requirements for this. This is followed by surgical implants. Usually titanium, stainless steel, different sizes and variants. Hearing aids, the parts we supply there, they are usually not visible for the end customer. Material what we use very often here is stainless steel, sometimes titanium. Pacemaker and painkillers are nearly always out of titanium because of the environmental. They are in the human body, and this is the material which have to be used there. Medical devices like inhaler, blood glucose meter, usually they run in high volumes, millions, yeah, very often. Orthopaedic, on the other side, high number of variants, and for each variant, low or middle quantities. Material also stainless steel, most of them. MIM magnets, sensors, and drivers for prosthesis, for example. I will show you later some examples for this one. And finally, instruments and parts for surgical robotic systems. The next two slides, I have chosen some advantage requirements where we think they are applicable for medical industry. The first one is, of course, single use. Single use is very important for us because single use means increased volumes, means increased cost pressure, of course, and this requires fully automated processes. Also, if we talk about increased volumes, this is very good for the MIM tool we have learned earlier. The costs are amortized more quickly. Another advantage requirement is the parts are usually very small. Of course, invasive surgical methods requires the smallest of instruments which can be reduced. The machining industry, yeah, of course, has difficulties with small sizes. They need small milling cutters. They are more expensive. Lifetime is shorter. On the other side, MIM and AM costs goes down due to reduced part weight and increased furnace loading. Precision, MIM and AM offers in a comparison, for example, to cast iron, much higher precision, and post-processing can be avoided. Parts identification traceability. We have a great possibility in regard of shaping the parts. And by using those technologies, we can offer cost-neutral solutions for part marking, for traceability, and part identification. Material, yeah, material that are difficult to machine, like titanium, etc., can be efficiently manufactured by MIM and AM. Design and functional integration. The integration of several parts into one results in the new solution concept, which gives you a competitive advantage. But the same gives you also a cost advantage because several parts, individual parts, can be combined into one component. The consistent use of MIM and AM results in new solutions because the high design freedoms you can offer, and AM offers even more design freedom. For example, inner contours that cannot be demolded by MIM. However, what is really important here to mention is that early involvement of our manufacturing specialists is needed. Yeah? We have to bring together your products and our technologies, and this can only be done in a dialogue. We can offer from our side 25 years experience in MIM and sinter-based technologies. Feel free. Now a comparison between the different manufacturing ways. This is a real part we have realized. This is a valve. Yeah. On the left side, you see a turn part conventionally manufactured. On the right part, on the right side, you see the MIM part. In fact, the turn part you produce 60% burrs and 40% only parts. MIM, AM, we have nearly 100% in the part. Save material, save resource, put your part on the diet. Try to utilize the design freedom of the MIM process to create lightweight parts. This will save material and costs. In fact, by using MIM, we had a weight reduction from 32 gram from a turn part to 23 gram of the MIM part. 29%. Feel free, use the possibility of MIM process to consolidate parts. Save assembly costs by making one part out of 3. integrate different functions into one single part. The picture top right shows the conventional solution. This part is assembled out of 3 pieces and connected by laser welding. The picture below shows the MIM part. It's now a one-piece solution. In fact, we have built a 8 cavity tool. So one shot gives you 8 parts. I mean, you can calculate by yourself what would be more efficient and what is more economical. No question about, I think. Feel free. Use the possibility of the MIM process to consolidate parts. These are some examples we think which would be some applications. For example, the production of one-piece drilling templates. I know that they are today manufactured out of plastic, printed plastic. Yeah? Why not do them in printed metal? Or another example is from the dental industry. Is again a drilling template, but this part is today assembled out of several parts. So combine all the parts into one. Non-demountable cavities. Use the freedom of design that only AM offers to you. The example is a curved cooling channel. Yeah. (2K) AM and MIM combine materials. 2K MIM inject 2 materials into the tool. The same with AM. Bring 2 different materials. Combine materials with different properties in the same parts. You have application which requires magnetic, non-magnetic. Combine 316 and 74 pH. You have application where you need high friction or temperature resistant. Combine Inconel on the functional area and cheaper normal steel for the support material. Of course, there are some technical limits. In this case, it's the sintering atmosphere and the sintering process itself. Both materials has to fit together. But no worry, our team will help you. But MIM and the M can also mix. So this example shows MIM and the M part. The green part you see on the bottom right is always the same. For every variant, this part is the same. But on the top, the nozzle itself, the valve, has different lengths, different geometries, etc. So why not combine it? The bottom part is MIM parts, high quantities, always the same. And the flexibility in the variants are produced by printing. Co-sintering, same process, combine 2 MIM parts. So the part you see on the right is a nozzle for injection system and it's really in high volume. So it is a MIM part, yeah, because of the quantities. But on the other side, there are undercuts in the assembly. So this part cannot realize technically in a tool. So what we have done now, we have built a tool with 2 cavities. So the right part and the left part. And after injection process, we take those parts and we assemble them together. We have a press fit in the green stage. Once they are assembled in the green stage, we go through the debiting and sintering. And during sintering, those parts are connected. The traditional way would be you have 2 parts and you assemble them by laser welding. Co-sintering, mix different processes, a combination of MIM and conventional manufactured parts. The part that you see here is a connector, and there are the tiny stainless steel tubes assembled. So when we had this request on front of us, the customer said, "Okay, we have a case, we have a chassis, and I will laser weld later these tubes inside." So we have thought about this. What you see here in this sketch is we have the green part. This is the injected parts. You remember we have approximately 20% shrinkage from the green part to the sintered part. So we inject the parts, then we assemble the stainless steel pins, and during the sintering process, the MIM part shrinks on the pin. And again, it's a solid, it's one piece then. So again, what we save is working step laser welding. MIM Clever, 2 parts out of 1 tool. The part what you see here has some really tight tolerances. We have a fitting tolerance on the bearing bore diameter and on the bearing bore width. So it was clear if we use MIM or AM, this part needs a secondary operation. So it was clear we have to do the machining. In the same way, we have a part for left and right. So what we are doing now today, we print the part, we cinder the part, and by the milling, when we rework the bore diameter and the bore width, we cut off the left or the right end of the part. So in fact, we have one cavity tool, but we can produce two different variants. MIM clever opportunities of green part processing. Some materials are really hard to machine. Green part processing is much easier. In this case, this is a finger follower for a sports car engine. The material is quite hard in the sintered stage. It has more than 50 HRC. Yeah. On the other side is 0.5 hole, which is here, is something which cannot be realized in the mold. In the injection process, we have pressures up to 1,000 bar. So a core with only 0.5 or in the green, 0.6 millimeter will not last very long. So what we do here, we inject the part, and in the green, we drill the hole inside. So we drill plastic. Yeah, and this is again much more clever than drilling into a steel, which has more than a 50 HRC. MIM magnets in medical industries. The idea is, the solution what we can offer is here is 100% waste-free production of complex shaped rare earth magnets. We have developed at MIMplus a process which starts from the recycling of end-of-life magnets. We mix our feedstock out of this material, we inject it in the mold, we do the binding and sintering, and at the end of the day, we can offer MIM magnets which are shaped from the MIM process with all the advantages we have, but we have the mechanical properties from a regular magnet. Yeah, of course, the application could be arm like this. By the way, this is the arm from Luke Skywalker. Yeah, so it's only a fake. Yeah, but the application is what we see as a height. Think green, MIM and AM are green technologies. Yeah, we have you see here the so-called feedstock. This is what we inject into the mold. Here you see how the parts look when they come out of the tool with the spurs. The only parts, the green parts, goes into the binding sintering, and the spurs are regranulated and reused again. Some samples, yeah. On the left, you see parts which are printed in our mold jet system. On the right, you see parts which are printed in the cold metal fusion. Of course, you see this layer by layer, yeah. But why we have chosen those parts? Because there are high variants, a number of variants required on this field. Yeah, the same is for screws, bone screws, for dental and surgical. The threads are printed. Yeah, and the idea is, or the solution with AM is produce parts which are ready to use. The same application could be, for example, drillers, bone drillers, for example. Yeah, bone drillers, they are offered usually in a high number of variants, different sizes, different lengths, different diameters. Yeah, from the mold, from the dimension, they are quite a complex shape. Yeah, and the idea is, or the solution could be to print the parts and just do post machining on the cutting edge. A comparison and example now between AM and versus MIM. The part you see in the picture right is a locking assembly. It contains two MIM parts, which are today produced out of stainless steel for 40C, which is hardened and coated. We have two machining parts, this axle and the housing here. We have a plastic part, which is the arm. We have a magnet, which is glued in the arm. We have a spring, some screws, some washers. In total, 11 sub-suppliers involved, and finally the assembly in-house. So the core competence of this part is those extender wheels. You see here yellow marked that there are undercuts. So the perfect solution would be to do it out of one piece. When we have started this project, unfortunately, we don't have AM technology installed at MIMplus. So we have chosen the conventional MIM way. So we have done it out of two pieces, and we have assembled it here in one. We have now started the process internal, and we have produced parts in mold shed and cold model fusion, which gives you even a bigger advantage. Yeah? The last example, AM versus MIM, these are two small parts, dimensions 4 mm, 2.5 and 5 mm. The internal channels and geometry are really complex shaped. Because of this, we can build only a 2-cavity MIM tool. On the other side, because those parts are so small, really a big amount of parts fit into one print shop. And this was something what was also fascinating for me, is that if the parts are that small and that complex for MIM, we can offer with AM a cost reduction of 20% or 60% for the parts below. But the good news last. You know the way you want to go. We know the car which has to be used. So MIMplus technology is your car dealer who selects the best vehicle for you to follow the way you like to go. That's from my side. Thank you very much for the attention.
Here again, the 4 webinars we held last year, just to repeat a little bit the topics we had back there. And if you think one or more of these topics are still interesting for you, then these can also still be downloaded from our homepage. So now we would like to say thanks again. We are looking forward to welcoming you again to our next webinars. We plan 2 more webinars this year. The topics will be luxury and aviation. And so have a nice time until then, and goodbye.
Bye.
Bye.
Bye.